Assalamu alaikum everyone. So welcome to the second part of the differentiation masterclass. So in the last class, what we did was we were done with point of inflection, which was our model number 12. So if you haven't watched the last video, I would totally recommend you watching that first before watching this one. Okay, so in this video, we are going to resume from where we left, and that is model number 13. All right. So give me a minute, please. Hmm, Okay. So without any further ado, let's start with model number 13. Okay, model number 13, that is equation of tangent. All right, model number 13, equation of tangent. So what is a tangent, right? A tangent is a line. A tangent is a line that touches the curve, that touches the curve or a circle just once. All right. So let's say we have a circle here and a curve here, right? A circle and a curve. So if I just draw a line that touches once, right? So this line that touches once is a tangent, right? If this line were to pass from here, it would intersect twice, and we don't want that, right? We want a line which touches the curve only once, and that line is a tangent. This is something you should already be know, or should already know, right? Because this is something basic. So in order to find the equation of this line, there are certain steps you should follow. So let's just write it down. In order to find the equation of tangent, the following steps are applied. The following steps are applied. Okay. So step number one. Step number one, calculate gradient or dy over dx. Calculate dy over dx, right? Step number two, substitute x coordinate, x coordinate of the given point in answer of step one. Step number three, the answer hence obtained is the gradient of the tangent. Step number four, using the gradient of the tangent obtained, and the point of tangency, and the point of tangency form the equation, form the equation of the tangent. Pretty simple steps which you might have already done in AS, right? So let's just do a question applying these concepts. So, right, we have a question here. Find the equation of tangent to the curve, tangent to the curve at the point at the point 2 comma 3, and the equation of the curve is under root 4x plus 1, right? So we have to find the equation of tangent. Just simply apply the above step. Step number 1, calculate dy over dx, right? So we have y can be rewritten as 4x plus 1, the whole thing power 1 upon 2. So just simply apply dy over dx, 1 upon 2, 4x plus 1 minus 1 upon 2 into differential of the bracket, which is 4. So we have dy over dx with us, right? And what was our step number 2? Substitute x coordinate, all right? So if we x coordinate is 2, so we just substitute it in dy over dx, we get the gradient of tangent. This point is 2, all right? So the dy over dx is, let me just calculate, 2 upon 3, all right? So we have the gradient of the curve, right? So, and we have the point 2 comma 3, and using these 2 points and the gradient, we can easily form the equation, which is y minus y1 is equal to m x minus x1, 2. 3y minus 3 is equal to 2x plus minus 2 to the 4, right? So 3y is equal to 2x minus 4. 3y is equal to 2x plus 5. Y is equal to 2x plus 5 upon 3. So this is the equation, or you could have just left it like this. All right, so this was our model number 13. Let's move on to model number 14, which is equation of normal. Model number 14, equation of normal. Let me see if I can grab a darker pen. Yeah, green works perfect. Yeah. So model number 14. So what is a normal? Normal is a line perpendicular to the wait, is a line perpendicular to the tangent at the point of tangency, at the point of tangency. All right, so let's say we have a curve here, right? We have a curve, and this is our tangent, right? This is our tangent. So the line perpendicular to this tangent at the point of tangency, which should be this line, which should be this line, right? So this line here is what we call normal, right? This line which you can see, black. All right, so how to find the equation of normal? The steps are quite similar to that of model number 13, but still we are going to write them again. Steps to find the equation of normal. And I hope you are copying alongside me, because you really need you really are going to need these notes later on. So I would totally recommend you copying as you watch this video. So steps to find the equation of normal. Step number one, again, the same step, calculate dy over dx. Step number two, substitute x coordinate of the given point, x coordinate of the given point in answer of step one. All right. Step number three. Step number three. The answer hence obtained is the gradient of the tangent. Is the gradient of the tangent, not the normal. All right. The gradient of the tangent. Step number four. In order to calculate the gradient of the normal, we have to reciprocate it. All right. So we will just write it negative, negative, reciprocate gradient of tangent, gradient of tangent to obtain the gradient of normal. Step number five, using the gradient of normal, using the gradient of normal and the point of tangency, and the point of tangency, form the equation of the normal. All right, so these are the steps you should be applying. All right, so let's have, so just let's take the previous question as an example. Let me just copy it. Let's just change it a bit. Find the equation of normal to the curve at the point 2 comma 3, and we have already calculated the gradient, right? So the gradient is 2 upon 3, right? We already know the gradient of the tangent, so uh, the gradient of the normal would be negative 3 upon 2, right? So dy dx of normal is negative 3 upon 2. All right, we have the gradient of normal and we have the point 2 comma 3. Now just simply form the equation. Y minus y1 is equal to m x minus x1. Right, so this is the equation, or you can write it like this, even better, right? So this was really easy, and these two concepts are something you should already know by now, something which you have already studied in AS, right? So another small concept, model number 15, small changes. All right, the model number 15. Model number 15. Small changes or approximate changes. Approximate change. Small change or approximate change. So let's start off by writing. If a small change, if a small change in x leads to a small change in y, or a small change in y leads to a small change in x, then the question falls under the category. Then the question falls under the category of approximate change or small changes. Approximate change. All right. And in order to solve such questions, we will apply the formula. Apply the formula. And this formula is this: dy over dx to small change in x, right? So where this sy is small change in x, small change in y, small change in y, and sx is small change in x, small change in x. All right. So we need to apply this formula when encountered with such a situation. So let's do a question as an example. All right. So the question is x and y are connected by the equation y is equal to 3x square minus 5x plus 12. All right. And x varies from 2 to 2.02. Find the approximate change. Find the approximate change in y. So we know the formula. The formula is small change in y is equal to dy over dx into small change in x, right? The formula we just learned. So let's just apply this formula. So let's first calculate dy over dx. We know that y is 3x square minus 5x plus 12. So dy over dx would be 3 to the 6x minus 5. So this is dy over dx. All right. And we need to calculate the small change in x. So as you can see, x changes from 2 to 2.02. So the small change in x is 2.02 minus 2, which is 0.02. So what would be the small change in y? So let's just calculate it. Small change in y is equal to dy over dx, right, into small change in x, that is 0.02. The small change in y is 6 into, you can see the value of x is 2, from which it changes to 2.02. So the value of x will be 2 minus 5 into 0.02. Small change is y. Small change in y would be 7 into 0.02, and small change in y is 0.14. All right. So now this was small change in y. Now the question can also ask you small change in x, for which you would have to simply uh, calculate small change in y and just shift the formula, play around with the formula to calculate the small change in x. So let's do that as well. Let's do a question with that. So the question says, given that x and y are connected by the equation y is equal to 9x to the power 2 upon 3, right? And y increases from 36 to 36.3. Find the approximate change. Find the approximate change in x. All right, so you have to find the approximate change in x. So first step, just write down the formula, dy over dx into small change in x. All right, so we have to calculate this. So the small change in y is 36.3 minus 36, and that is 0.3. All right, and dy over dx, let's calculate that first. So y is 9x power 2 upon 3. So dy over dx would be, to multiply by 9, 9 into 2 upon 3 is 6, 6x, 2 upon 3 minus 1 is minus 1 upon 3. We have dy over dx, right? So now we have to play around with this formula to calculate y is equal to 9x 2 upon 3. We have the value of y, which is 36. 9, see this, 36. 9x 2 upon 3 is equal to 36. So 4. All right. And if we just multiply it by 3 upon 2, so we get x is 8. All right. So we get the value of x, which is 8. Now just put this here. All right. So dy over dx is 6x8 power minus 1 upon 2. So dy over dx would be, wait, what did we, um, this was supposed to be minus 1 upon 3, right? Because we deducted 1 from here. My bad. Right, so let's do it. 6, 8, 3. So we have dy over dx 3. Now just simply apply it into this formula. All right, we have small change in y, which is given in the question, which is 0.3. And dy over dx is 3, and we need to calculate small change in x. So small change in x would be 0.3 divided by 3. The small change in x is 0.3 divided by 3, 0.1, right? So that's it. Okay. So let's move on to our next model, right? Model number 16. Model number 16. And that is rates of change. Rates of change. So just start writing. If one variable, if one variable changes with respect to time, with respect to time, and causes the other variable, and causes the other variable to change with respect to time, to change with respect to time as well, then the question falls, then the question falls under the category of rates of change, falls under the category of rates of change. And in order to solve such questions, and in order to solve such questions, we need to apply the chain rule. We need to apply the chain rule. Let's let's do a question as an example through which we would understand. All right, so just simply write the question. So the question says the radius of circle, the radius of circle is increasing, is increasing at the rate of, at the rate of 0.5 centimeter per second at the instance, at the instance when r is equal to 3.5 centimeter. Find the rate, find the rate of change of area. All right, so you can see the question says the radius of a circle is increasing at the rate of 0.5 centimeter. What does this mean? This means that dr over dt, which is the rate, is 0.5. All right, and r is 3.5, and we need to find the rate of change of area. We need to find dA over dt. This is what we need to find. And we know that the area of circle is pi r square. Through this, we can calculate dA over dr. All right. So 2 pi r, which is 2 pi r, right? So now we are required to find the rate of change of area, right? Rate of change of area, which is dA over dt. So we will now form a chain rule. And how do we form the chain rule? This is how we form the chain rule. We just write like this, dA, and in the next denominator we write dt, and then we write, and then we put a common variable here. So in our case, the common variable is dr. All right. So we will just put dr over here. Okay. So dA over dt is dA over dr, right? We have already calculated dA over dr. That is 2 pi r into dr over dt. Dr over dt was given in the question, which is 0.5. And we have the value of r, which is 3.5. So dA over dt would be 2 pi r 3.5 into 0.5. All right. So 2 pi r into, let's just do this, 2 pi 3.5 into 0.5, and that is dA over dt is 10.995 centimeter cube per second. All right, and in exams we always leave answers up to 3 significant figures, right? So it's going to be 11.0 centimeter cube per second. This is going to be our answer. All right. So let's do another example of this. So write another question. All right. Okay. The rate of change, the rate of change of radius of a sphere is 1 upon 4 centimeter cube per second. Find the rate of change of volume and area of the sphere at the instant when radius is 7 centimeter. All right. So the rate of change of radius of a sphere is 1 upon 4. All right. So one thing to understand here is whenever mention the rate of change, just write dt in the denominator. All right. When you read this word rate of change in the question, right? And then it says the rate of change of radius of a sphere, right? Radius. The radius is what? dr, right? So dr over dt. This is a key tip from my side, right? So we know that dr over dt is 1 upon 4. All right. And what do we need? Find the rate of change of volume and area of the sphere. Volume and area. So let's find out the rate of change of volume first. So a volume of the air, the formula to calculate the volume is 4 upon 3 pi r cube. And if in case you don't remember the formula in the exam, you can always refer to the MF19 formula sheet, which is provided to you. All right. So you don't need to be worried about that. Okay. And usually the question also gives you the formula here if required. So again, you don't need to worry about that. Okay. So dV upon dr would be 4 upon 3 into 3 is 4 pi r square. All right. And we know the radius, which is 7, right? So dV upon dr is 4 pi 7 square. So dV upon dr is, let's just assume pi to be 22 upon 7 for the sake of this question. All right. But you should always keep putting the exact value of the pi. Okay. So 4 into 22 upon 7 into 7 square, which is 616. All right. So dV over dr is 616. And we know that we have dr over dt provided. And what do we need to calculate? Find the rate of change of volume, right? So we need to calculate dv upon dt, right? dv upon dt, which is the rate of change of volume. So simply again form the chain rule, dv over dt, right? You write it in this specific format, and the common variable is dr, right? So just write dr here and dr here. All right. So we have dv over dr with us. dv upon dt is equal to dv over dr, which is 616, and dr over dt is provided to us in the question, 1 upon 4, right? Into 1 upon 4. So dv upon dt is going to be 616 into 1 upon 4, which is 154 centimeter cube per second. So this is dv over dt. Now the question also asks for the rate of change of area of the sphere, for which we would have to form a different chain rule, of course. All right. So we have dr over dt, which is the same, which is 1 upon 4. But the area, the formula to calculate the area of the sphere is 4 pi r square. All right, 4 pi r square. So dA over dr would be 8 pi r. All right, we have dA over dr, we have dr over dt. So now there should be no problem in forming the chain rule, right? The rate of change of area dA over dt is what is required, right? So just form the chain rule. dr is the common variable, all right? dA over dt. We have dA over dr, which is 8 pi r, and dr over dt, which is 1 upon 4. We also have the value of r, which is 7, right? As provided in the question. So dA over dt is going to be 8 pi 7, right? 8 pi 7 into 1 upon 4. And again, for the simplicity of this question, I'm going to assume pi to be 22 upon 7. But remember, in paper, you only have to use the exact value of the pi. All right. So if you are going to do 22 upon 7 in the paper, the examiner is not going to give you any marks for that. All right. So 8 into 22 into 1 upon 4, we have 44 centimeter square per second. This is our rate of change of area, and this is our rate of change of volume. So I hope this model number 16, rates of change, is crystal clear. And of course, with practice, you're going to get the hang of it, because this chain rule is something you will be encountering not just in differentiation, but throughout. Uh, yeah, but I think only in differentiation, I guess. Yeah, this chain is rule is something you would be encountering quite frequently in recent past papers, especially, right? So it's better it's important you get the grip of it. All right. So without any further ado, let's jump on to model number 17. Okay. Model number 17. Just give me a minute before we start. Okay, so yes, model number 17. Model number 17. Maxima, minima. All right. Okay. So let's start writing. So if a geometrical figure, if a geometrical figure with two unknowns, with two unknowns is being considered, is being considered, and we are provided, and we are provided with its perimeter, with its perimeter, area, and volume, right? And we are told, and we are told to express to express one variable in terms of the other variable, and are also told, and are also told to find the stationary values, to find the stationary values of the variable, values of the variable, and to determine its nature, and to determine its nature. Then we will apply, then we will apply maxima minima as follows. All right. So let's again let's just understand with it and understand this with the help of a question. All right. So I'm going to write the question and through which we will understand this concept. The dimensions, and believe me, this is not a new concept. It's something you already know. The dimensions of a rectangular box, of a rectangular box are 2x into x into h. All right. And and perimeter is equal to 72 centimeter. So part 1, express h in terms of x. All right. So for a proper visual, I'm going to, you know, draw a box here. So this is a rectangular box. All right. 2x, x, and h. These are the dimensions of this box. So what we are told to express h in terms of x. So the perimeter is given to us, which is 72 centimeters. All right. So just calculate the perimeter. So 2x, so 4 times 2x, first 2x, 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 right? 4 times 2x, perimeter is 4 times 2x plus 4 times x, right? Plus 4h is equal to 72. All right. This is the perimeter. All right. And 12x, if we just add this up, 12x plus 4h is equal to 72. So just play around with this equation. 4h is equal to 72 minus 12x. So if we just also simplify this equation, right? So 4h is equal to 4 times 18 minus 3x. So h is 18 minus 3x. All right. Through the equation of the perimeter, we simply expressed h in terms of x, right? And I really hope you understand this because it's a very basic concept involving the use of perimeter. All right. So, okay. So part two we have, which says express volume in terms of x. Express volume in terms of x. So we know that volume is length into breadth into height. All right. So volume is going to be 2x into x into h, 2x into x into h. All right. So volume is going to be 2x square into h. We know that h is 18 minus 3x, right? So volume is going to be 18 into 2, 36 x square into 6x cube, right? So this is the volume. Now, part 3. Part 3 says, given that given that the volume varies, given that the volume varies, find the stationary value of x. Find the stationary value of x and h and determine its nature. And determine its nature. All right. Right. So we need to determine, given that the volume varies, find the stationary value of x and h and determine its nature. So we know the volume is 36x square minus 6x cube, and the volume varies, which means we have to calculate dy over dx, which is 36 into 2, which would be 72x minus 18x square. And we need to find the stationary value of x. So in order to find the stationary value of x, we are going to equate it with 0. All right. So 18x square is equal to 72x. All right. So x is equal to 72 divided by 18. X is equal to 4. And since we have cancelled x out, x is also equals to 0. But notice one thing, that 0 in a question involving volume and areas, the length can never be 0, right? So 0 is automatically going to be rejected. All right. We would reject 0. All right. So, so the answer is x is equal to 4. And this is the stationary value. This is the stationary value. All right. And we are also told that we have to find the stationary value of h as well, right? So h is, so stationary h, we calculated h, which is 18 minus 3x, right? So 18 minus 3x, we are going to insert the value of x, which is 4, into this and simply calculate h, which is 18 minus 3, 4, and h is 18 minus 3, 6. All right, this is the value of h. Now, we also told that we need to determine its nature. So, in order to determine its nature, we need to calculate d square v upon dx square. All right, so we already have dy over dx with us, right? Which is 72x minus 18x squared. And now we are going to differentiate again in order to calculate d square y upon dx square, right? So which is 72 minus 36x, and we have to calculate the nature of this stationary point we calculated. All right. Now just insert this into the equation. 72 minus 36x, which is 4. All right. So 72 minus 36, 4. D square yx is minus 72. All right, which is less than 0. And whenever d square y over dx square is less than 0, the stationary value is maximum, as we learned in the previous models. All right. So this is the nature of the volume that varies. All right. So let's move on to another model, model number 18. So now I believe here onwards things are going to get a bit interesting, right? So you want to pay more attention. So model number 18. Model number 18, right? Wait. Uh, Model number 18, differentiation applied to exponential function. Differentiation applied to exponential function. All right. So what is an exponential function? This is what an exponential function is, right? So what would be dy over dx? Simply dy over dx would be ex for this. All right. So let's say we have another exponential function y is equal to e ax. So dy over dx would be e ax into a. All right. So as a general rule, you should remember that y is equal to e power fx. When y is equal to e power fx, dy over dx is equal to e fx into f dash x. All right. So that's what's happening here. E fx, y is equal to e power x, dy over dx is e fx into f dash x, and differential of x is 1. So it's pretty much the same with no, and so dy over dx is pretty much the same, right? And here as well, when y is equal to e power ax, dy over dx is e ax into differential of fx, which is a. All right. So, and here y is equal to e fx and differential is, and dy over dx would be e fx into f dash x. So this is the rule that you should be remembering, right? This is what you should remember. All right. Now let's do a couple of example questions for this one. All right. Y is equal to e 7x. So dy over dx would be dy over dx would be E7x into differential into f dash x. So dy over dx is 7e7x. All right. So when y is equal to e12x minus 3, right? So dy over dx would be e fx into differential of fx, which is 12. All right. So dy over dx is 12e 12x minus 3. All right. So similarly, if y is equal to, let's make a more complicated equation, um, a quadratic, right? 2x minus 1, right? So same rule is being applied here. Dy over dx is e x square plus 2x minus 1 e f x into f dash x. 2x plus 2. So dy over dx would be 2x plus 2 e x square plus 2x minus 1, right? So this is how you differentiate exponential functions. I hope everything is clear. Now moving on to logarithmic functions. Logarithmic functions. All right, that is our model number 19. So model number 19, differentiation, differentiation applied to logarithmic functions. All right, so I will start off with a general rule this time. All right, so when y is equal to ln fx, differential would be, a general rule is that dy over dx would be 1 upon fx into f dash x. All right. So this is the general rule that you should be remembering, right? So let's just apply this rule and solve some questions. Okay. So let's say y is equal to ln 5x. So dy over dx would be 1 upon fx, which is 5x, into differential of fx, which is 5, right? So it is 5 upon 5x, right? 1 upon x if you simplify it. All right. So another question. Y is equal to ln 8x, right? So dy over dx would be 1 upon fx into f dash x, which is 8, right? So it is going to be 1 upon x as well, right? So this is how simple it is to differentiate logarithmic functions. You only should remember this general rule. Okay. So moving on, model number 20, which is differentiation applied to trigonometry function, right? Model number 20, differentiation applied to trigonometric function. All right. So we have y is equal to sin x, y is equal to cos x and y is equal to tan x. So how are we going to differentiate them? So you have to remember that dy over dx would be, when you differentiate sin x, you get cos x. And when you differentiate cos x, you get negative sin x. And the differential of tan x is sec square x. This is what you should remember. All right. This is something you should remember. Differential of sin x is cos x, and differential of cos x is negative sin x, and differential of tan x is sec square x. All right. So, if we have, let's say, y is equal to sin ax, y is equal to cos ax, and y is equal to tan ax. So the differential is going to be dy over dx is equal to sine, the differential of sine x is cos x, cos ax into differential of this, which is a. All right, so it's going to be a cos ax. Similarly, y is equal to cos ax. Differential is, as we learned, cos x has a differential negative sine x. So we are going to write negative sine ax into differential of this, which is a. So it's going to be negative a sine ax. All right. And similarly, dy over dx of tan x is sec square ax and multiplied by a, which is the differential of fx. Right. So dy over dx would be a sec square ax. All right. So as a general rule, you should know, let me write the general rule therefore. Right. So when y is equal to sine fx, dy over dx is equal to cos fx into cos fx multiplied by f dash x. All right. When y is equal to cos x, the differential is negative sine fx into f dash x. All right. When y is equal to tan fx, dy over dx is equal to sec square fx into f dash x. All right. So this is something you should be remembering. All right. When we are going to do some questions involving trigonometric functions, stuff is going to make a lot of sense. All right. Model number 21. Model number 21. Differentiation applied. Differentiation applied to trigonometric functions. To trigonometric functions with higher powers. With higher powers. All right. So just simply know that whenever you are differentiating trigonometric functions with higher powers, let's say sine x is equal to power n. So you're just going to treat it like normal differentiation, right? There's no need to get confused. just treat it like a normal differentiation. So dy over dx is n comes down, right? Sine x n minus 1 into differential of this bracket, as we learned in the earlier models, right? So this is how you differentiate them. Okay, so let's take an example when y is equal to, let's say, sine square x. All right, so dy over dx would be 2 sine x, 2 minus 1 is 1, into differential of the bracket, which is sine x, into which is cos x, right? So dy over dx is 2 sine x cos x. All right, and let's say if we have cos cube x, all right, dy over dx is 3 cos 3 minus 1, right? Square x into differential of the bracket, right? This cos x, the differential of cos x is negative sine x, right? Like I said, the key here is to just treat it like a normal function, the way you treat normal functions, the way you differentiate them. All right, 3 sine x, negative 3 sine x cos square x. Let's say we have y is equal to 2 sine 5 7x. Wait, 2 sine 5 7x. Let's just write it again first for the sake of simplicity. 2 sine x 7x power 5. All right. So just differentiate like you would differentiate a normal function. 5 comes down, it is multiplied to 2, 10 sine 7x, 5 minus 1, which is 4, and to differential of sine 7x. The differential of sine 7x is cos 7x into differential of f, right? Into 7, like we just studied here, right? Sine fx, cos fx into f dash, all right? So what we simply did here is we just differentiated as we would differentiate a normal function. 5 comes down here, 5 to the 10, sine 7x, 5 minus 1, 4 into differential of the bracket, sine 7x, which is cos 7x into 7. All right. So dy over dx is 70 sine for 7x cos 7x. All right. So this is the differential. All right. So I'm going to hold till here, right? Now what's left in differentiation is we are left with only 6 models, right? Only 6 more models are left. All right. And I want to make a separate detailed video on this because these are really, really important models, right? These are the most complicated models of this chapter and the most important as well. So I want to do a different separate video on this one. All right. So that's going to be part 3 of this differentiation masterclass series. All right. And then we are also going to solve some past paper questions. So get hold of the models studied till now first, right? Revise them and subscribe this channel, like them, like it. And there's one thing I would like to say here, if you like the quality of our content, right? In the donation, in, in the donation section in the description, there's an account where you can donate. There's an account mentioned where you can uh, donate to us to support our cause of free education for all, right? Okay, take care. Allah Hafiz, and meet you in the next video.